Hi, everybody. So I realize I'm coming a little close to the 4 p.m. time that I said I'd have all the videos up by. So clearly I'm really good at managing my time. But I wanted to go kind of supplement the last video with maybe like one or two little extra propositions. So this will be a lemma. So we saw before that a basis can generate a topology on a set. So this is sort of going backwards, where you have a topological space, and you have a collection of subsets, and you want to know when that collection of subsets is a basis for the given topology. So this is kind of working backwards. When a given collection is a basis for a topology that you already have. So this is a collection of subsets such that for all opens U in X, and for all points X in U, there exists some element, say C in script C, such that X is in C, on script C, which is a subset of U. So again, this is sort of the exact same like local criterion that we've been looking at a few times now. So C satisfies this property. Then if that holds, C is a basis for X comma tau. That is, the topology generated by C is the same one given by tau. So the fact that C is a basis isn't really too hard. So proof. So almost kind of by assumption, C is a basis for a topology on the set X. So it generates some topology. Maybe call it tau prime on the set X. Right, because remember before, for our definition of basis, X was just some set, and B was just some collection of subsets. So C generates some topology, and the only question is whether or not it's the same topology we started with. So how do you find that out? So we claim, or we wish to show, I'll abbreviate that a lot. We wish to show that tau is equal to tau prime. So to that end, let U be an element of tau, so an open subset of X. So by assumption, I can write U as a union over all X and U of these elements C sub X. And, well, this thing is going to be inside tau prime. by the definition of a topology generated by a basis. So this is one direction. We've just shown that tau is a subset of tau prime. Likewise, let W be in tau prime. Well, all that means is that it's a union of elements in C. But by assumption, these things are all open. And so W belongs to tau. So we're done. It's just a quick little lemma. It's nothing really deep here. It's just kind of going backwards. So I want to make kind of more rigorous this little thing I was drawing before. How I can compare two topologies on bases. So just kind of reminiscent of what we did last lecture, comparing different topologies like coarser and finer and so on. So we have another lemma. Let B and B prime be bases for the topologies, say, tau and tau prime, respectively, on a set X. Then the following are equivalent. Oops, we abbreviate that as TFAE. The following are equivalent. 1. Tau prime is, other way around. Tau prime is finer than tau, which means this. Tau prime has more open subsets than tau does. And 2, for all x, and x, and for all b in script b with x inside b, there exists another basis element b prime in script b prime such that x is inside b is inside b prime. So this is just saying, I can always find another basis element containing my other one. So these two are equivalent. The proof of this is relatively straightforward. I'd actually suggest maybe trying to work through it on your own. But what I want to show is specifically on that example I was just doing. So let's look at my one basis of opens. Maybe I should make this a little bigger. I'll make that like here. So here's my x, and here's my basis element b. So what this says is that I can always find another basis element in the other. So this here I'll do, this will be open balls. And this one will be open rectangles. Well, clearly, I can just make a bigger open rectangle that contains this thing. Pretending, of course, that this page is a substitute for the real plane. So since x was arbitrary and so was the ball of B, this tells me what? The limit says that the topology generated by the open balls is coarser than the topology generated by the open rectangles. But this game can play the other way. If I look at x and maybe I'll keep the same thing. I have some open rectangle, B prime. I can just find a bigger open ball that contains that thing. Since x was arbitrary and so was the rectangle that contained it, this tells me the other thing is true, that tau prime is coarser than tau. But that can only hold if they're equal. So this means that open balls and open rectangles generate the same topology on R2. And like I said, it is worth kind of going through and actually proving this on your own. It's quite simple. It's like, I think like 3 or 4 lines. All right, guys. I will see you again on Friday.